So probability histogram. So this is going to be really just based off probability distributions, and this isn't really anything too new for us. So we're just making histograms based on those probability distributions. So you think of this as more of a relative frequency histogram. In essence, they're essentially the exact same thing. Probability distribution, so probability is a little different than you talk about relative frequency, but not too much different. So a probability distribution can be represented by histograms to visualize the distribution. So the following represents the probability distribution and histogram for the number of heads in a sequence of 5 tosses, using the assumption that heads and tails are equally likely and tosses are independent events. Okay, so if we are tossing 5 coins, there is a chance that we are going to get heads or tails, using the assumption that heads and tails are equally likely. Number of heads, okay. So we're likely to get 0 heads, 1 heads, 2 heads, 3 heads, 4 heads, 5 heads. Now, what you're going to have here is one time, it's really like 1 out of 32 times you get 0 heads. So all this is reflecting is that this is just 1 out of 32, or 0.03125. So all we're doing is we're just doing probabilities here. So instead of saying relative frequency, we just put probability. So we're going to have our random variable here, which in this case is number of heads. And our probability. So everything is exactly like a relative frequency histogram. And once again, so 1 head, that would be, I think there's 4 ways that will happen out of 36. But all we're doing is we're just showing those probabilities. Or 32, I'm sorry, not 36. That's 5. Okay, there's 5 different ways to get that. So we're just seeing, like I said, this is 5 out of 32. And then this is 10 out of 32. So we're just still representing those, like I said, relative frequencies. It's just that we're writing them as proportions this time. So we want to make a histogram of the sum of dice rolls. So remember, what goes along here is probability. Probably should write it the other way. It is not easy to write sideways. And then what we have down here is this is the sum of 2 dice rolls. So sum of 2 dice. So we can either get 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We need to write our probabilities. So my largest probability was right here. So I'm going to probably scale this to here. So we're going to have 0.1 here, 0.2 here. So 0.02, 0.04, 0.06, 0.08. I'm just winging this a little bit, so it's not perfectly to scale. And then we have 0.1, 0.12, 0.14, 0.16, and 0.18. So like I said, nothing's too different so far. So just like with the histograms that we did before, we're going to start at the 2 and make the bar after that. And we just go up to about roughly here, because that's just a tad under 0.023, because we need 0.028. The 3 would be here, so we go up to a little over half between 0.05 and 0.06. So my 4 is at about an 8. So starting at 4, we go up to a little past 8, and then we go over. And then we do 5. 5 is a little past, right here. And we get 6. So 6 has 0.139, so almost 114. And the 7, that is 16, almost 16, 0.17, so roughly here. And then after that, the rest of it's like symmetric in this case. And that's just what my distribution will look like. And then just don't forget that we have to end it here. So that 13, but we're not going to really write it there. So I'm going up by 2s. So that's all it is. That's all we have to do to make a histogram from a probability distribution. Okay. So that is how we used to do them. Just to point this out, so there's a little change they make here. Oops. So just to show you that, and sometimes in this case, so this was something we could do with histograms all along. It's just that we hadn't done it yet, is we can actually mark in the center this time. So before we always had to like start after the number because we're like doing like those bins. But a lot of times when we have discrete numbers, we'll just put a number in exactly in the middle to represent it as well. So like I said, this is something that changed a little bit from something we were doing in the past, and it's not a big change here. So as you saw here, we put the 0 exactly in the center of each bar. The same thing here, we put the number in the middle of each bar. So this is just reading. Following is a probability histogram for the number of children a woman has. We want to know, what is the probability that a randomly chosen woman has exactly 2 kids? So here's 2 kids. So that probability of having exactly 2 kids is 0.244. Next part is, what is the probability that a random woman has fewer than 2 kids? Well, this right here is fewer than 2 kids, 0 kids or 1 kid. So this is a case when we start using these random variables that instead of saying something like a less than 2, I might actually start writing things like x. X is my random variable, x is less than 2. Or up here, instead of writing just 2, I might say x is equal to 2. And that probability is this. So just something to bear in mind that you can see it written like this as well, that sometimes instead of just writing the words or just putting a number in, we might actually put like a little equation or a little inequality. So less than 2, that is going to be 0.273 plus 0.16. So we're going to have the 3, 6, 7, that's 13, 2, 3, 4. So that is going to be 433. And then the last one was the probability that a randomly chosen woman has either 4 or 5 kids. So my random variable is 4 or 5. So that represents this right here. So that is 0.082. So chance of 4 kids is by 8%. The chance that you have 5 kids is almost 4%. If I add those together, the 1, carry it, 8, 9, 10, 11, 12. So we get, we're getting, oh, yeah, we're going to get 0.121 or about 12%.